Okay, so we have seen what effect, if any, applying an elementary row operation has to the determinant of a matrix. And recall that we can think about applying elementary row operations by multiplying by elementary matrices. So for example, here is a 4x4 elementary matrix where we basically have the identity matrix, but in row 3, we have multiplied by 5. So the diagonal entry across row 3 is 5. And so here you could very quickly justify that the determinant of this matrix is the product of these diagonals, which gives us 5. And so if I call this elementary matrix E1, then what we can see is the determinant of the product of E1 and A, in this case, actually equals the product of their determinants, is going to equal the determinant of elementary matrix E1 times the determinant of matrix A, since we know that applying E1 to matrix A has the effect of scaling one of the rows by 5. And we've shown that that effect would multiply the determinant of the original matrix by 5. And now we just showed that this elementary matrix actually has a determinant of 5. So here we've shown that at least for elementary matrices, if I take a product of an elementary matrix, which is a scaling operation on the left, times some matrix A, that the determinant is going to equal the product of the determinant. So I can take the determinant of that scaling matrix and multiply it by the determinant of the original matrix A. And let's see what happens with some of the other elementary operations. So if I do an interchange of two rows, so here is the identity matrix, which has had row 2 and row 4 interchanged. So this is also an elementary matrix. And here you could verify that the determinant of this matrix is -1. And we can justify that in the following way. If we do a cofactor expansion across row 1, there's only one non-zero term. So we would get 1 times the determinant of the submatrix over here. And now we could do a cofactor expansion along the, say, third row of this submatrix. And what is remaining would be 1 times the determinant. And here, since we only have one non-zero term when we do that cofactor expansion, we only have to account for one of these submatrices. And this 2x2 matrix would have a determinant of 0, -1. So altogether, this determinant of this matrix is 1 times the determinant of this, which is -1. And that gives us that the determinant of this elementary matrix corresponding to an interchanging of rows has a determinant of -1. And so similarly here, we can see that if I apply this operation to some matrix, I'll call this E2 for an interchange, then what we're going to get is minus the determinant of that matrix. And here we can see that this is equivalent to saying I could take the determinant of matrix E2 and multiply it by the determinant of matrix A. So again, we can see that at least for elementary matrix, the product of an elementary matrix times some matrix A, the determinant of that product is equal to the product of the determinants. And one last operation to consider, and that would be a row replacement operation. And we've seen that a row replacement operation should not have any effect on the determinant of a matrix. So for example, applying a row replacement operation to the identity matrix shouldn't change its determinant. We should still get a determinant of 1 since the determinant of the identity matrix is 1. And now let's verify this, calculating the determinant, say, using a cofactor expansion across row 1. And row 1 is nice because we have only one non-zero entry here. So we're going to get 1, and then we only need to worry about one submatrix. So we're going to get 1 times the determinant of this 3x3 submatrix. And now to calculate the determinant of this 3x3 submatrix, we'll pick this entry over here, there's only one non-zero entry in the top row, so we only need to worry about one submatrix that we get. So it's going to be 1 times the 1 times the determinant of this submatrix, and this submatrix is now the identity. So this gives me 1 times 1, and the determinant of this matrix is 1. So we can see here, doing a row replacement operation on the identity matrix, we verify that this doesn't change the determinant. And so with row replacement, we get another similar result, namely that if I take the determinant of the product of a row replacement operation on the left times some matrix A, we can write that as the product of the two determinants, since we showed before that this doesn't change the value of the determinant. And so over here, we showed that this determinant is equal to 1. So therefore, the determinant of the product of E3 and A is going to equal 1 times the determinant of A. So just to summarize these 3 points all together, that if E is any elementary matrix, then the determinant of E times some matrix A, where we're going to assume A is a square matrix so that this product makes sense, we can calculate this determinant by calculating the determinant of the elementary matrix E and then multiplying by that by the determinant of that matrix A that we started with.